All right, so this is the question. If f of x is equal to x to the nth, then what's f prime of x? We want to find a general rule for a derivative, and in this case, this is going to be for powers. For example, we won't know what the derivative of sine is. We won't know the derivative of e to the x is from this, but we will at least know the derivative of, say, x to the fifth. And you guys came up with 5x to the fourth. Some of you guys have seen the pattern. We'll show you what happens here. We're going to set it up. The limit is h goes to 0 of f of x plus h. Okay, I'm going to pause this right now. Okay, one less student. There we go. All right. Good times, good times. All right. So limit is h goes 0 of f of x plus h. So I plug in x plus h, and I get x plus h to the n minus x to the n all over h. Now, I want to be clear here that, sometimes people see this stuff, they're like, well, I don't really like the proofs. Some people really love the proofs. They want to see it work all the way out. And this is where you're heading in mathematics to be able to accomplish this type of work. And this is a very basic proof. There's nothing wrong with it, or nothing that bad with it. I'm going to expand this out, and I'm going to expand it out using Pascal's triangle. And if you notice, we have x plus h to the nth, so what's going to be the first term? X to the nth. Then, forget about the coefficient right now. X to the n minus 1, very good. And an h. Then, and second. And eventually we would have just an x squared, right? Or like, I'm saying like, say an x and an h to the n minus 1. And then an h to the n. So we would have that kind of stuff, okay? And then we have to subtract off, because I'll be there in a second. And then what are we going to subtract at the end? All over h. So I've expanded Pascal's triangle. I've expanded the binomial. Now, using Pascal's triangle, I'll insert the coefficients appropriately. Please look over here at the coefficients. Do you notice a pattern? For example, you have the first power, and then the second power, third power, fourth power, fifth power, sixth power, seventh power. What is always the first coefficient? 1. What's always the second coefficient? Whatever power it is. So what power is this? N. So what's going to be the coefficient here? N. I'm proving this shortcut for you. This is not the end result. This is your beloved algebra, so just... is there necessarily a pattern that we can write for the third one? Not really. We'll just call it C for some coefficient. And then by the time we get to the very end, you can see that the h to the n is going to have what as a coefficient? 1. And then the x h to the n minus 1 will have a coefficient of n. Okay? All right. What cancels? X to the n's, and then I can divide off an h from the rest. So I'm going to do that right now. Everybody see that the x to the n's cancel. Then let's divide off the h. So I will be left with n times x to the n minus 1. Does it have an h anymore? No. Plus a constant times x to the n minus 2 times h, plus a bunch of stuffs that all have an h in it, right? So I'll just put that, remind us that they all have h's in them somewhere. Plus n x times h to the, if you divide it off an h, now instead of n minus 1, you're going to have n minus 2, plus, and now if you divide an h off of the h to the nth, you're going to have h to the n minus 1. Okay, so can I now let h go to 0? I can let h go to 0 because it's not in the denominator. So if I let h go to 0, what's going to happen with this guy? 0. What's going to happen with this guy? 0. What's going to happen to everything in the middle? 0. This one. 0. This one is the only one that's left. So you get n times x to the n minus 1. So our question from the beginning was, suppose that your function is x to the n, then f prime of x is equal to n times x to the n minus 1. You guys don't seem excited enough. Watch. If f of x is x to the 5th, what's going to be the derivative? You take the exponent, you drop it in front, and do what to the exponent? 5x to the 4th. Suppose you got x to the 8th. 8x to the 7th. Suppose you got 4x to the 3rd. 12x squared. 6x to the 5th minus 2x to the 4th plus 3x squared minus x plus 1. What's this one going to be? 30x to the 4th. Oh. Because if you have negative x to the 1st power, drop that out here and reduce it by 1. So you have negative 1 times x to the, what's 1 minus 1? 0. And what's anything to the 0? 1. So negative 1 times 1 is negative 1. Think of it, you guys. Negative x is a line, right? And it has a slope of negative 1. Okay? 1 is a line. What kind of line? A horizontal line. What's the slope of a horizontal line? 0. So the derivative of a constant will always be 0. The derivative of something in the 1st power will always be the coefficient because that's the slope. So you can see how quickly we could take derivatives of powers, polynomials. I mean, that's remarkably fast. However, you know, we want to be able to do something like this eventually. Sine of pi times e to the x squared, you know, all of a sudden, you know, it goes out the window. Or suppose you want the derivative of 4 times, you know, 3x plus 1 to the 40th power. Well, you want to multiply it out 40 times and then do the power rule? There's a way to get around that too. And that's what we're going to teach you in the next unit, is how to get around some of these things. But at least you know the power rule now. If I give you the function 3x squared, what's the derivative of 3x squared? 6x. Look at that. Now, some people say, why don't you teach us that to begin with? I can teach my 9-year-old daughter to do that. And she doesn't know calculus. Your job is to know calculus. No. Knowing that the derivative of 3x squared is 6x, she has no idea what the derivative means, and you still don't say that. You still don't know what derivative is. Oh, voter off the island. You're gone. Hey, yeah, I'm recording. Okay, so hey, you right there. Okay, you say you still don't know what it means. I'll tell you what. Here's something that my daughter doesn't know either. And this is what we waited 2,000 years to find out, you guys. Look at that. Some people are you're not writing that when you're doing your work. This limit piece is what makes calculus possible. You know, it's that what we did. I'm done with you. What? Well, in the 1600s, 1500s, that's when calculus was formally written down, by Isaac Newton and his colleagues. So about 400 BC. Yeah, already they were putting together ideas about infinite, collection of shapes, sizes, and like I said, when Archimedes was around, Archimedes in the year 200 BC, he had already formalized a lot of what we know about calculus. The problem is it wasn't able to be expressed mathematically in a way that we could really work with. This formal idea of a limit was pretty tough, to be able to write down. And when it finally came together, then calculus is what we know it to be now. But like I said, we went through a long time where they were more interested about art and philosophy and religion and literature instead of mathematics, and that halted mathematics. Get, this symbol means about. Are we okay with that? 2,000 years. Okay? So if it was 1600 and it was around 200 BC that Archimedes was around, so we'll give a negative sign to that one. Yeah, but this idea, this development of, I mean, yeah, we have caveman inscriptions that show they were able to count to 3, but they weren't anticipating anything like this. So, already in the year 600 BC, the Babylonians were using trigonometry to try to map the orbit of the moon and stuff like that. I mean, they were doing that stuff. So, but before that, nobody was anticipating or waiting for calculus to develop. Well, I should say it, that we know of. That we know of. But yeah, aliens. Yeah, there you go. Okay, that's all I got for you.